Let me start then. I'm on the right-hand side of the screen, David Berglund. I'm the co-founder, together with Carl Fengco, of Ainomaly software. We've been a part of Mobility X Labs for a couple of years now. Petter, hand over to you.
So my name is Petter Belander. I work at Fengco, real-time control as an application consultant, and the main business at Fengco is that we are distributors for dSPACE in Sweden.
Yes, hi. So I'm Carl Fengco. I'm the CTO at Ainomaly.
Thank you, Carl. So what we are going to tell you about today is how a project where we've demonstrated how we conduct 10 years of testing in 165 hours using existing tool chains as well as modern active machine learning, which is relevant for both ADAS and full AD application development. Brief background to who we are. Carl and I are co-founders of Ainomaly, a company that is founded on some research that Carl and his team have conducted at the Royal Institute of Technology. And Fengco, as Petter mentioned, are experts in V2V for the automotive industry and have almost a quarter of a century of experience in the automotive industry. The project that we've been doing was part of the Chronos 2 initiative. Many of you are probably familiar with that, where we partnered with Volvo Cars as well as Volvo Trucks. And our part of the project had two specific aims. One was to demonstrate extensive scenario-based testing in a fully virtual environment. And the other one was to show how that could reduce physical testing, reduce cost, and reduce time to market for complex autonomous functionality. The use case that we're going to show you in a video in a minute is for adaptive cruise control. And the environment that we used to implement this was the dSPACE ASM validation and verification SIL toolchain. So let me show you a brief video of what we've shown.
The future of automobility is near, and car developers must adjust to new technology, like autonomous driving. Fengco and Ainomaly have created a new solution that makes autonomous driving software safer. Fengco provides tools for developing and testing algorithms, offering the possibility to simulate complex traffic scenarios with dSPACE Automotive Simulation Models ASM. ROBOTest from Ainomaly uses active machine learning to test and validate ADAS and autonomy applications. The biggest challenge on the road to autonomous driving is building confidence in the algorithms that take over from the driver. For this, driving must be simulated in challenging scenarios. Fengco and Ainomaly have now integrated ROBOTest with the dSPACE ASM in a new software-in-the-loop toolchain to show how AI-powered anomaly detection copes with the complexity of real-world traffic situations. This gives new possibilities for faster and cheaper development and homologation of safe autonomous driving. Ainomaly's smart machine learning algorithms explore the multitude of variations for each scenario, helping you to identify the critical parameters. Our toolchain enables you to generate critical test cases in a software-in-the-loop environment that can later be reused to test the final implementation on a hardware-in-the-loop simulator, improving the return on investment of your testing infrastructure. Through our collaboration, you can streamline your testing of AD and ADAS to develop safe, autonomous vehicles for the future. Ainomaly and Fengco are your partners in development and testing.
Very good. So what we want to do now is delve into three areas that this video touched on. First of all, the active machine learning component of this, which is what we call ROBOTest. Secondly, the SIL environment from dSPACE called ASM. And thirdly, the benefits that have come out of this. So what ROBOTest allows you to do in your full AD or ADAS development is to conduct tens of billions or even hundreds of billions of use cases. Now, the data point on the left of this screen is taken from Waymo, who before they went live with their robo-taxi initiative in Phoenix, Arizona, conducted 19 million kilometers of on-road testing, but 8 billion kilometers of simulated testing. And that is proof that without simulated testing, fully autonomous vehicles will never be possible. Now, conducting hundreds of billions of kilometers is great, but only if you are testing the right kilometers. So what ROBOTest does is it applies active machine learning to map out the complete state space and make intelligent choices about which are the edge cases that need to be tested, hence delivering complete scenario-based testing in a much reduced time than if you were to do this with any other method, especially random or even manually. So in this diagram, you can see obviously a cut-in scenario, as was described in the video, and then a very simple block diagram of what ROBOTest does. And it takes requirements that are defined for the software that's under test, and from that delivers a set of anomalies or bugs based on the search and find algorithms that it conducts as it iterates through every scenario that it deems important to do so for. Let me hand over to you, Petter, as we go into what the tool chain that we've integrated with is.
Thank you. So the dSPACE automotive simulation models here, which are open models that simulate vehicle dynamics, drivetrain, and traffic scenarios, and we use them for verification of ECU behavior in closed-loop simulation. So traditionally, this has been used in real time on hardware-in-the-loop simulators, but today it is increasingly used in software in the loop, which can be scaled up to the cloud, which is essential to get the coverage needed to build confidence in this AD or ADAS algorithm. The models are built from the beginning to be parameterizable, so that the simulated vehicle and foremost the road and the traffic scenario can be changed during runtime. So for AD and ADAS testing, focus lays on the traffic simulation and the sensor data. But we still need an accurate simulation of vehicle behavior, which includes vehicle dynamics, driver, and some ECUs. We also need an environment, a road network with surroundings, and this can be generated within the tool, or it can be imported from map data or some standard interface like OpenRoad. And then it comes to the traffic simulation. The traffic simulation will contain relevant traffic objects that should be detected, such as vehicles, traffic signs, buildings, etc. And also a scheduling how everything should move, a scenario. So in order to test the device under test, then we need to simulate it with data. And if there are perception algorithms included in the device under test, we can also generate realistic sensor data for camera, LiDAR, and radar, which we generate with advanced sensor models and 3D simulation techniques such as ray tracing. And in parallel to the sensor models, we also have ideal sensors that provides ground truth data so that we can determine if the detection works as expected. Yeah, so this is just a select number of published customers all over the world. As you see, we have a lot of the major OEMs, and if we would use the unpublished customers as well, the list would be rather extensive, even in Sweden. So what we did in this project is we integrated ESM with ROBOTest from Ainomaly. And the reasons for this, what is the use of testing environment if it's not utilized to verify your requirements? And finding the critical scenarios and parameter sets is not an easy task. In this project, we integrated these tools to help us with this. Now we can use the results from the previous simulation runs to find a new parameter set and for the scenario and identify the edge cases where the system and the test fails. So through an iterated process, ROBOTest learns more and more about how the system and the test behaves and can challenge it where weak spots are identified. Yeah, I think I'll hand over to Carl now.
Thank you, Petter. Thank you, David, for the next slide. So these are some of the performance results that we got from the Chronos 2 project. We actually analyzed 4 different use cases for the ACC product, and we analyzed them in road models varying between 2 and 4 vehicles. As David's mentioned, one of our most impressive results is the compression in time. So we're doing testing in a virtualized environment provided by Fengco, the ASM simulator, and we can, for example, overclock the simulator so we can run faster than real time. And we can also create multiple copies of the simulator so we can run pieces in parallel. So if you put all that together, you can get an acceleration values up to something like this. What would take 10 years out on the road can be done in 165 hours in a virtualized environment. So I think that really motivates the value of using simulation-based testing. And we can see some other performance figures down here. We have estimated that if you take into account the time to write test cases and execute them and hand them back to the development team, we can get a 9 times reduction versus manual testing. If we look at the overall product costs, we think we can get a 4 times reduction in testing there. If we look at the test velocity, that's just the rate of throughput of tests, we see figures up to 250 times increase. That's on a scenario basis, and if you look at that on the individual tests themselves, it goes up to 700 times. So the high degree of automation that you can achieve from ML shows up in very many different ways. So we see that feeding through to the development case and the business case in, amongst others, these 5 ways here. So we test the write kilometers. We do that by constraining testing with a model of the use case. And in particular, the machine learning takes that boundary description and sort of zooms in on the specific edge cases, which are very sensitive, possibly even safety critical, by allowing overclocking of the simulator and parallel simulation. We get massive scalability. So this is a solution that would work well in a cloud environment. We see that customers can enhance their existing investments. We don't just generate new test cases. We can take on board your existing legacy test suites. The whole thing gives significant improvements in productivities in some of the ways we saw on the last slide. And of course, the whole point of doing testing and increasing the test throughput is to reduce the errors and to reduce any residual risk inside the product. David, I'll give that back to you.
Okay, thank you very much, Carl, and thank you, Petter. So obviously this last slide is for questions and answers. If there are any questions, then please type them in the chat field. And what we're also trying to do with this final slide is just to emphasize the sort of productivity improvements that you can have by using a fully virtualized SIL environment and enhancing that with active machine learning test case creation using synthetic data for high throughput simulation. Hopefully you found this valuable and interesting, and if there are any questions, we will be happy to answer them. Has written in the chat, do you experience the customers are happy with the test catalogs they already do have and only ask about the speeding up the testing? Wow, that's a great question. Carl, perhaps you could answer that in terms of the work we've done for NCAP, where I think the answer is yes. And then maybe Petter, perhaps you have some more experience of that?
You know, testers are always worried about coverage. Most of the test suites that we see, they're handwritten, and that takes time. In fact, we've had statistics of maybe half a day per test case. So anywhere between an hour and perhaps half a day. And it's clear that when it takes so much time to write just an individual test case, you're not going to get many hundreds or thousands of these things constructed. There's neither the time nor the money. And I think it's this coverage that people are very sensitive about. They'd like to get their coverage levels up. So it's not that they have bad tests already, but they want more. They want to be able to convince their managers, and eventually we feel that they will want to pass homologation certification, which surely is coming in. It exists to some extent with NCAP, but I think we're going to see a lot of it more with things like ISO 262. So there will be, I think, a relentless pursuit of better and better coverage. That's what we see in other industries, and I think it's coming to automotive. Peter, do you have anything to add to that?
Well, I can just add one thing, and it's from coming from traditional domains and powertrain or vehicle chassis development or anything. Then, I mean, you have requirements and you know how to test them. But coming into AD or ADAS, then suddenly, yeah, it should always behave good. But how do we get the coverage, as you said? It's both hard to measure the coverage, but then especially hard to. There's so many variation points. It's basically indefinitely amount of variation points. So we need some kind of help here to say what do we need to verify, what can we vary, which variables should we touch, and what can we do to get the coverage up.
And so we need to wrap up here, but Carl, just very briefly, why does ROBOTest guarantee high quality?
ROBOTest guarantees high quality because it's automated, it's a verified system in itself. You can describe your use case very precisely, and you can be sure that what you're seeing from what's going on inside the software.
Thank you very much, Carl. With that, I think we'll wrap up and go back to the main session.
Thank you, David.